Femoral popliteal artery is the main artery in the upper leg which distributes the blood to the superficial tissue in the thighs and muscles. Femoral artery stenosis restricts the blood flow through the lower limb due to the presence of the plaque. Therefore, the treatment of the artery can be cured with a stent. Stent is a tubular wire mesh used to treat narrowing and weakening of blood vessels. However, after a few weeks of stenting procedure, the restenosis or reblockage of the artery can occur due to the growth of atherosclerosis or thrombosis. The experts predicted that the stent STRUT geometry had a major contribution of restenosis process. Stent STRUT geometry plays such a key role in the restenosis process and has a relationship with the velocity, pressure, and wall shear stress distribution near the stent STRUT geometry. In methodology section, they are consist of 5 steps. The first one is simplified geometry of central femoral popliteal artery model, which consists of stent A, stent B, and stent C. The second one is mesh generation as stented femoral popliteal artery model. The mesh type generation is tetrahedral mesh of computational domain. The parameter assumption and boundary condition used are incompressible nucleus. The density is 1000 kg per meter cube. The viscosity is 0.0035 Pascal, and the condition of the vessel is rigid and no slip condition between the vessel and the stent. Next, the discretization technique is by using two equations, which are the Navier-Stokes equation and the continuity equation. Last but not least is the analysis. The analysis is to analyze the pressure, velocity, and wall shear stress distribution throughout the simplified artery model. Project verification. Verification is the process of verifying the numerical results for both current and previous studies. This process is compulsory to ensure that the method used for numerical simulation was in agreement with the other simulation. The comparison of simulation results was analyzed based on the previous study. This finding was used as a reference for verifying the previous study by calculating the relative error. From the calculation, the relative error is approximately 7.8% and acceptable due to the pattern of the results quite similar as illustrated in the figure. The results for pressure and velocity for different types of stents. The occurrence of the stenosis due to the high blood pressure in an artery can be treated by implanting a medical device called a stent. The shape of the STRUT cross-section also gives an effect to the hemodynamic parameters of velocity and pressure distribution. The pressure and velocity change for all stages of the STRUT. The pressure becomes higher and the velocity becomes lower after passing the STRUT. This happens because the qualitative behavior that is usually labeled term benign effect is the lowering of the pressure in regions where the flow velocity is increased. Figure 6 shows the distribution of wall shear stress for different stent STRUT configurations. From the observation, they are the formation of vortices due to the flow recirculation, especially at the distal region. From the calculation, the total wall surface area in a range greater than 7 to 9, which was approximately 30% for type A, 23% for type B, and 15% for type C. The development of stenosis process is influenced by the direction of flow passed through the sheet of stent STRUT configuration. The main factor that influence the growth of stenosis are thrombosis and atherosclerosis. The formation of thrombosis and atherosclerosis can be predicted numerically based on hemodynamic factors. the wall shear stress value is greater than 70 dynes could lead to the formation of thrombosis. In a conclusion, the best stent performance is type C. Type C shows the less total wall surface area percentage compared to type B and type A. Thus, essential shapes, configurations, and design of the stent should be acknowledged in order to lower the risk of atherosclerosis formation due to growth of thrombosis. The novelty and inventiveness of this product is managed to establish the best hemodynamic stent performance, and the flow is aligned with the flow direction and can reduce the growth of thrombosis due to the flow direction. Thrombosis may cause hardening of the arteries, gradual or rupture of the arterial wall, and eventually complete blockage or a reduction of the blood flow. Therefore, the usefulness of this product can be held open by placement of stent to promote normal blood flow. This is a photo diagram for stent A, stent B, and stent C. The experts predicted that the stent STRUT geometry had a major contribution of the stenosis process. Stent STRUT geometry plays such a key role in the stenosis process and has a vital relationship with the hemodynamic factor near the stent STRUT geometry. This STRUT configuration, developing based on hemodynamic performance, was seen as commercialization potential. A patent is an exclusive right granted for an invention based on intellectual property cooperation of Malaysia AR21 innovation of stent STRUT configuration. This stent STRUT configuration in general a new way of doing something or offers a new technical solution to a problem, especially in reducing the risk of stenosis in femoral popliteal artery.